Welcome to qnawire.
For letter A, we need to find H if the impulsive reaction at point C is 0. So for letter A, we're looking for H. So I have here a sketch of the problem. So our system here consists of a bullet and the bar. So the length of the bar is L, so it's given, so 30 inches. And H is unknown. So the weight of the bar is given, so it's 15 pounds. And then the weight of the bullet is 0.08 pound. So in the problem, the bullet with a mass m sub b, small letter b, and a speed v sub o equals 1,800 feet per second approaches the lower end of the bar, which is at rest, so at point B. So since the bar is initially at rest, we have here I omega 1 equals 0. Now, so that's you can see that in the first part of our diagram or sketch. Now, in the second part, so the bullet becomes embedded at point B, but according to the problem, the impulsive reaction F at point C is equal to 0. So that's the second part of the sketch. And then the last part, so when the bullet is embedded, it caused the bar to rotate, giving it a non-zero angular momentum, so I omega sub 2. And because of this, point B and point G, which is the center of the bar, rotates with respect to point C. So with velocities V sub B and V sub G respectively. So that's V sub G and V sub B. Sorry, I forgot to put it in the diagram. Okay, so there. So that's our setup. Now, before we start with the computation, so let's first convert the values to feet. So the values in inches to feet for consistency of units. So L is 30 inches. So multiply this by the conversion factor. So 1 foot is equal to 12 inches. So cancel. So we'll have 2.5 feet. And then in our computations, we'll not be needing really the weight of the bar and the bullet, so we need their mass. So we also have to calculate for the mass of each. So from the given weight. Hence, our mass of the bar is weight sub B over G. So the weight of the bar is 15 pounds, and then the equivalent of the acceleration due to gravity in feet per second squared is 32.2. So this will be equal to 0.466 pound second squared per feet. And then for the bullet, so mass bullet equals weight of the bullet over G. So that's 0.08 pound over 32.2 feet per second squared. So that's 0.00248 pound second squared per feet. So those are our given values. So to solve for this problem, we will apply the relationship between the torque experienced by the bar and its angular momentum, which is given by the expression summation torque equals the change in angular momentum over the time interval. So substituting the equation for torque and for angular momentum, so this will become, so summation, so all the forces times the lever arm, then angular momentum is, change in angular momentum is I omega 2 minus I omega 1 over delta t. So we can actually cancel this out since, as I've said earlier, the bar is initially at rest. So that's basically our equation. Now, for the left-hand side, we'll write the equation for the net torque about point B. So why did we choose point B? Because it would be less complicated. The equations will be less complicated because, if you recall, we don't know the value of H. So we'll treat B as our pivot point. And then, so since we have F here or force here in our equation, so take note that the force is not given, but we can actually get this from the relationship between force and linear momentum, which is given by, so F equals the change in momentum over the time interval, so which is equal to M delta V over delta T. As for the right-hand side, we can replace I, which is the moment of inertia, with 1 over 12 times the mass of the bar, L squared. So since the bar is a rod, so that's the moment of inertia for a rod. So 1 over 12 mass of the bar, okay, L squared. So our equation will be, M mass of the bar V sub G over delta T, so times, so the distance from G to B is L over 2 since G is at the center of the bar. So L over 2, okay, equals the final angular momentum, so which is 1 over 12 mass of the bar L squared omega sub 2 all over delta T. So notice our equation is simpler because we set B as our pivot point. So we can cancel out T here as well as M sub B. So that will be our equation. Now, substituting the given values. So again, we'll omit the units for simplicity. So we'll have V sub G, which is unknown, times 1.25 equals, so 1 over 12 times 2.5 squared omega sub 2. So simplifying the equation, so we'll get VG equals 0.521 omega sub 2 over 1.25. Okay, so this is equal to, so V sub G equals 0.4168 omega sub 2. So this is our equation 1. So we cannot solve yet for the unknown. As you can see, we don't have H in our equation. So we need to have another equation. So since V sub B and V sub G here are linear velocities, so we can express them in terms of R and omega. So using the equation, V equals R omega. Hence, VB is equal to So L minus H omega sub 2 because though we chose point B as our pivot point, so the bar is actually rotating at point C. So V sub B or point B is L minus H away from point C. So that would be the radius. So L minus H omega 2, so that would be 2.5 minus H omega sub 2. So that's our second equation. And then for V sub G, so V sub G, so G is at the center. And if you can see from the diagram, so G is L over 2 minus H away from point C. So L minus 2, or L over 2 minus H omega 2, so that would be, so 1.25 minus H omega sub 2. So this is our third equation. So we now have three equations, and if you'll notice, we already have H in our equation. So we can equate since since equation 1 and equation 3 are both for VG, so we can equate these two, and we'll get so 0.416 omega sub 2 equals 1.25 minus H omega sub 2. So omega 2 will be cancelled for both sides. So we'll have H equals 1.25 minus 0.416. Sorry, this is 4168. Okay? So therefore, H is equal to 0.833 feet. Now, if you want to have it in inches, so because the original values are in inches, so that would be so 0.833 feet times the conversion factor. So 1 foot is equal to 12 inches. So this will be about 10 inches. Okay. So H is 0.833 feet or 10 inches. Now, for letter B, we need to calculate the angular velocity of the bar after the bullet was embedded. So, that would be our omega 2. So, to solve for this, we will apply the impulse momentum theorem, which states that the change in momentum is equal to the impulse. So, since according to the problem, the impulse is 0, so it means that the initial and final momentum of the system are equal. Hence, our equation would be, so the initial momentum is only for the bullet, so mb times v sub o. Then the final momentum is for the point G, center of the bar, and for point B, so the lower end. So that would be the mass of the bar times Vg, and then plus mass of the bullet Vb. So substituting the values and the other equations that we have, so this becomes 0.00248 times 1,800. Again, we're omitting the units for simplicity because the equation is long. So equals 0.466 times 1.25 minus 0.833. So we'll use the feet equivalent of H. since 1.25 is also in feet. Omega 2, then plus 0.00248 times 2.5 minus 0.833. So, this will become 4.464 equals 0.1943 omega 2 plus 0.004134. So, further simplifying the equation, so we'll have 0.1943 omega 2 equals 4.464. So, omega sub 2 equals omega sub 2 equals 4.464 over 0.1943. So that's equal to about 23 rad per second.